A very good evening, everyone present over here. I welcome you all to our tea talk, which is the 34th tea talk of CAT. So today it's my great honor to welcome Dr. Ajit K. Mahapatra sir for our talk. So today's webinar will explore the use of intense pulse light IPL as a non-thermal method to inactivate E. coli on Salmonella on pecan herbs and quantify microbial reduction while assessing effects on key quality attributes and overall food safety compliance. So a brief background of sir I would like to give that currently sir is joining us from USA. Sir is currently a professor of food engineering at Fort Valley State University, USA, in a seasoned academic and an authority in non-thermal food processing and food quality safety innovations, a proud alumnus of our college from 1981 batch. His academic qualification include a MS from IIT Kharagpur in the year 1983 and a PhD from Hungarian Academy of Sciences, Budapest in 1991. Prior to joining FVSU, he worked at the South Dakota State University, USA, Botswana University of Agriculture and Natural Resources, and the University of Zambia. Uh, then he has various global experiences also that has enriched his perspective on food systems and processing challenges and cultural approaches to food, bringing a truly international industry relevant lens to his work. His work on innovative inventions to control foodborne pathogens has been published widely. When he is not helping jab pathogens with advanced technologies or teaching his students, he is seen enjoying gardening, reading, or a good Hollywood movie. So I welcome Dr. Ajit Mahapatra sir to this talk today. So you can continue with your presentation now.
Sir, you are muted.
Okay. Can you see my screen now?
Yes, sir.
Okay, good evening to you all, and thank you so much for the nice introduction. And so I don't have to talk much about me now. You gave a very good introduction, and so let me start. So topic of my presentation today is inactivation of E. coli and Salmonella by intense pulse light on pecan herbs. As you know already, I am a professor of food engineering at the Fort Valley State University. So it's based in Fort Valley, which is about 90 miles south of Atlanta in Georgia, state of Georgia. So let me start with what is non-thermal processing actually. What is the definition of non-thermal processing? It's a set of food storage, sterilization, or pasteurization techniques that is used to destroy or inactivate microorganisms, basically pathogens and enzymes. It can improve shelf life. It means the set of processing methods to maintain fresh-like quality, flavor, texture, and nutritional value. So all these processes takes place at or near room temperature using mechanical, electromagnetic, or light energy rather than using high temperature. So what are the non-thermal processing? There are various non-thermal processing methods. That's UV light, intense pulse light. That's what I am going to talk about. Cold plasma, irradiation, high pressure processing or HPP, pulse electric field, ultrasonication, and etc. So they can be used alone or in combination. UV light can be used with cold plasma, irradiation can be used with IPL, so they can be used alone or in combination. So this is the non-thermal processing technologies that we see here: high pressure processing, ultrasonication, called plasma, pulse electric field, pulse light, irradiation, and they are used for different, food functionality, molecular interaction, food structure. So what is intense pulse light actually? It has got various names like pulse UV light, PUVL, BSPL, high intensity pulse UV light, HIPL, or PWL, that stands for pulse white light. It produces short duration of very intense pulse light. It's like the intensity is almost like 50,000 times the intensity of sunlight. The light energy is produced by the excitation of inert gas. Normally, xenon is used with a high electrical voltage. So it produces very intense light, like, as I said, 50,000 times more than the sunlight. So this is the IPL system. You can see the schematic diagram. So there's a control panel, this pulse UV light, chamber, with the chamber where we put the food products, then the UV lamp is at the top, and it's got a window, and there's cooling floor. It is a power supply, capacitor, and pulse controlling system. So for this, we use a AG1000 modular sterilization system. It generates about 505 joules per pulse, or 500 joules per pulse, with a duration of 360 microseconds, and delivers 3 pulses at 1.3 joules per centimeter square from the light source at a distance of 1.9 centimeters. So inoculated pecan samples will be placed here in the chamber, and each treatment will be conducted in triplicates, and all the experiments were repeated twice or 3 times. So this is the spectrum of pulse UV light. So you can see it with the entire spectrum actually: UV light, visible light, blue light, UVC, UVA, red light. So it covers the entire spectrum actually. Yes, not like only UVC, which has a spectrum of like 200 to 280 nanometers. But this one, pulse light, is consisting of UVC, UVB, UVA, visible light, and infrared. So basically from 100 to 11,000 nanometers. So it is effective against virus, bacteria, fungi, and as well as parasites. So what is the mechanism actually? How it kills the bacteria or fungi, or so basically there are 3 types of mechanisms, or 3 main mechanisms, and they work in combinations actually. They are photochemical effect, photothermal effect, and photophysical effect. So what happens during photochemical effect? The UVC component, particularly 200 to 280 nanometers, causes the DNA mutation and damage the microorganisms, similar to just like the conventional UV. That means the cells cannot grow. They just start to die actually, so they cannot multiply. 2 cannot become 4, 4 cannot become 8, so basically they cannot multiply. Next one is the photothermal effect. So as we know, it produces a very high intensity light. So the high intensity pulse causes rapid and localized heating. So it produces some heat actually in the food product. Okay. So localized heating the microbial cell and the surrounding surfaces, so that destroy the cell, microbial cell. The last one is photophysical effect. The intense short duration pulse can cause physical destruction of cellular structures. So what happens in the cell structure? It ruptures. Okay. So that means you get a dead bacteria or virus or parasite. Yes. So why should we go for IPL? It has got the highest germicidal power, not powder, I'm sorry. It is produces low temperature. It is not like high temperature process. Yes. It's environmentally friendly because it doesn't leave any residues. And it has been approved by FDA, that US FDA, Food and Drug Administration, to use in food processing. So what are the different IPL applications? Falsibilite, it can use for food sterilization. It can be used for bottle and food cup sterilization. It can be used to extend the shelf life or storage life of foods. It can be used for medical devices to sterilize and also aseptic food packaging. Yes. So let's go to pecan. Why did we choose pecans actually? They are very commercially valuable crop. It has got even global significance. I thought there are about 500 varieties of pecans, but yesterday I came to know that there are 1,000 varieties of pecans, and they are harvested in late September. The height of the tree can be from 21 to 30 meters, and the width can reach about 23 meters. And each tree produces about 31 to 68 kilograms per year, a mature pecan tree. The US and Mexico accounts for about 85% of the world production and exports. So, and Georgia, my state, contributes about 50% of the US production. And it has got a very, very big global market actually. In 2024, it was about $1,960 million. Yes. And we are projecting that it will rise or grow 7.4% from 2024 to 2029. So if my math is correct, in 2029, we'll have a $3,000 million global. So this is how the pecan tree looks like. I don't know if you've seen a pecan tree probably not. These are insult pecan, then these are pecan hearts. So this is what we are working on. Pecan. So let's look at the pecan nutrition facts and health benefits. I have compared with cashew nut because cashew nut is popular in Orissa. So I thought, let me just compare. Yes, the taste is like sweet and buttery, and it has got about 690 kilocalories for 100 grams. Protein is 9 grams. Fat is 72. Carbs 14, and fiber is about 10 grams. Yeah. So it's very beneficial for health. It can control blood sugar, supports weight loss, it protects health of heart, and also reduces the risk of cancer. So what's the relationship with Georgia pecans and India? So India is now, as you know, it's a rapidly growing market for US pecans, and we export to India about 1.3 million annually. Recently, USDA invested about 24 million to boost Georgia pecan exports, specifically to India. So it's all 24 million only to increase the export to India, actually, yes. And we are projecting that we'll increase it from 1.3 million to 5 million export of pecans to India. So right now we are exporting only cell nuts, but we are not allowed to export insult pecans. So we are trying to work with government of India so that we can also export insult pecans. So tree nut safety, basically they are low activity foods. You know, water activity is less than 0.7. That means it's low water activity. But there are few pathogens of concern. Salmonella, E. coli, and Listeria are the main ones. And there have been few outbreaks in the US and worldwide linked to different types of tree nuts, yes. Because pathogens can survive for a long period of time. And contamination can occur at any stage during harvesting and processing. So how they harvest pecans is they try to stack the branches or the tree, and then the pecans when they fall on the soil on the ground, and then they collect it. So there is a possibility of microbes, getting from soil to the pecans. So these are the main microbes: Salmonella, E. coli, and Listeria. They are concerned for any tree nuts, actually, not only pecans. So I am not going to go through the table. There are a few outbreaks associated with nuts and nut products in 2021, 2024, 2022, and 2020. So let's go to the materials and methods. What methods and materials we will use actually for our experiment? So basically we use, some basic microbial processes in the lab. So first we prepare the culture, either Salmonella or E. coli. So we use non-pathogenic varieties of pickles or strands of E. coli and Salmonella, yes. So stock consoles were prepared from pellets dissolved in peptone water, sticked on TSA, and incubated at 37 degrees centigrade for 24 hours. Then what we did is a single colony was transferred into 10 milliliter of TSB, that is tryptic soya broth, and incubated for 37 degrees Celsius for 24 hours and stored in 0.5 milliliter of sterile glycerol, 50% volume at minus 20 degrees centigrade or negative 20 degrees centigrade. So whenever we required, the frozen stock was strict on a TSA plate, incubated at 37 degrees for 24 hours again. Prior to experiments, a single colony was transferred into 10 ml TSB and incubated again for 37 degrees for 24 hours. The culture was centrifuged at 3000 for 10 minutes at 4 degrees centigrade, and the cells were retrieved and they were resuspended in 5 milliliter of peptone water, that is 0.1% peptone water. So what we got is the initial concentration of E. coli or Salmonella was about 6 to 7 log CFU per milliliter. CFU stands for colony forming unit. Inoculation of pecans, actually. So what we did is pecan halves. These are the pecan halves. They're bought from a local store, or we got them from the U.S. Department of Education. Sorry, USDA research station. So we randomly selected the pecans. We took about 2 grams. Then we 40 microliter of inoculum were dispensed randomly at 4 different spots on each pecan half. Then we dried the pecan halves for 30 minutes so that we can have the attachment of bacteria to the pecan surface. So they were dried for 30 minutes under the hood. Now coming to the IPL treatment, as I said that we use a VCU1000 sterilization system, and inoculated samples were exposed to IPL in triplicate. So we use they were treated for different treatment times and different distances actually. And we have a control, that means untreated samples. So for Salmonella, we treated them for 10, 20, or 40 seconds. For E. coli, 1 to 15 seconds. And the distance was 8.3 to 13.4 for Salmonella and 4.5 to 9.4 for E. coli. These are 2 different experiments, and we have published papers. So if anybody is interested in, I can send it to them. That's why you see different distances and different treatment times, yes, because these are 2 different experiments. So we use 3 pulses per second and 1.3 joules per centimeter square per pulse at a distance of 1.9 centimeters. So here we have the light, and these are the pecan samples. So here you can see this is the pulsalized system. These are, we did in triplicates. These are pecan halves. They are placed on petri dishes, and then they were treated with a T1, T2, T3, so 3 different samples of pecan halves. So this can be moved. You can vary the distance from this is the light source, so you can always move the tray up and down. So that you can change the distance or vary the distance. So then comes the microbial analysis. So once the pecans were treated, we did microbial analysis. So we did serial dilution. Then we spread them on petri dishes. So we have a very automated lab. We use automatic spreading. We don't do it by hand. So here you can see it on the petri dish. We spread. Then it was incubated. The plates, petri dish is incubated 37 degrees for 18 hours. 18 to 24 hours actually, because for 18 hours is for Salmonella and for E. coli for 24 hours. So after 24 hours, we try to count the colonies. So what we did is we counted them in the beginning. Beginning means that before treatment, and then we counted them after treatment. So then that's microbial analysis. We also did physical properties analysis, like we measured the moisture content. So I'm not going to explain it. All of us, we know how to measure the moisture, right? Yes. So basically, we ground them into using a mortar and pestle, and so that they become thin powder. Okay, so thus we can increase the surface area. Then we use this equation to measure the moisture content. We also use, also measure the water activity. So all of us, we know what is the difference between moisture content and water activity. Water activity is the amount of water which can be used by microbes. So if a food product has 60% moisture content, it doesn't mean that all 60% can be used by microorganisms like E. coli or Salmonella. And water activity varies from 0 to 1. Okay, if it's 0.2, then it's very difficult for any microbe to grow in 0.2. And if it's 0.9, then the microbes will have a field day actually. So this is the equipment we use, aqualog water activity meter, to measure the water activity. We also measure the color actually, if the pulse UV light had any effect on the color of the pecans. So we use the Hunter's Lab color meter, or color meter. So we basically we measured or determine L, A, and B values. So the pecans were placed here at this port. Then we measured at 3 different places for each pecan. So what are this L and A? B stands for? L is light versus dark. So if you have 0, that means it's black. If it's close to 100, that means the color is white. Then we have A, is red versus green. Its negative value means it is towards green, and we have a positive value of A means it is towards red actually. And B is yellow versus blue. Its negative value means it is trending towards blue. Positive, then it's trending towards yellow. Or more yellow actually. Higher B value means if you get a very high value B value, that means is the product is yellow in color. We also measured the texture so that to find out if the IPL has any effect on the texture of the pecan. Did it change? Did it change, become firm, or it become hard? So we use a shear blade. You can see the shear blade here, and it was allowed to cut through the pecan. Okay, so we use, these are the technical information. We use a load cell 50 kilograms, the speed of the blade, this speed of the blade, it moves from here to here down, 4 millimeter per second, deformation or 20 millimeter, and trigger force we use for 0.15 Newton. We also measured that peroxide value because pecans are very high in unsaturated fats, so therefore there is a chance of oxidative degradation, which produces bad odor, bad flavor, and also it turns brown, internal browning actually when you try to store the pecans. Therefore, that's why we measured the PV peroxide values, just to know that if there are any lipid oxidation. That's a key indicator of freshness, quality, and rancidity. Yes. So we use the AOCS method to determine the peroxide values of pecans. Then finally, we did statistical analysis. Data were collected in triplicate, at least minimum triplicate. The colonies were converted to log 10 values because the colonies are in millions. Okay, so to have a standard, analysis using ANOVA, you need to convert them to log values actually, and they are expressed as means or averages plus or minus standard error. ANOVA was used to determine the statistical significance of the effects of treatment, that is effect of distance, effect of treatment time on the product. And Tukey-Kramer test was conducted to determine the difference between means at p is less than equal to 0.05. And we use SAS to analyze our data. So here are some results. You can see the first one is Salmonella reduction. So we could reduce from one log to almost 4.4 log. That means we got a reduction, if we convert the log to percentage, we got a reduction of 92% to almost 100%. CFU is colony forming unit, and one log is 90%. So when we talk about microbiology, when we talk about one log means that it's 90%. That means if initially if we had 100 E. coli or Salmonella, then you apply pulsivy light or UV light or an irradiation or whatever, and you kill 90 E. coli and you are left with only 10. So that is 1 log. 2 log is 99%. 3 log is 99.9%, and it goes on. So you can see here that, at 10 seconds, when the treatment time is less, we have lower reduction. And when the distance increases, it reduces the E. coli or Salmonella reduction. Yes. So this is the reduction in on y-axis. On x-axis, we have the distance in centimeter from the light source. So this is about E. coli. So you have different distances, 4.57 and 9.5 centimeters. And on y-axis, you have the E. coli reduction actually. So you got a reduction of starting from 24% to almost 99%. Yes. If you reduce the distance from the light source and increase the treatment time, significantly increase the log reduction. So whether you increase the treatment time or decrease the distance from the light source, that will give you a higher reduction. So we choose the optimal reduction of 2.06 because there were some pecans were charred or they got burnt. So this was our optimal distance and treatment time where we got 99%. So it was 2.06 log. We also did fluorescence image so to look at the intensity of viable E. coli decreased when pecans were treated with IPL. So if here you see less green light, it indicates that there were higher E. coli reduction is. But we also found that some, pecans had some crevices, the gap in between, so the E. coli could hide actually. That's why we could find that some E. coli cells from the IPL treatment, they could hide in the crevices. Color, hardness, moisture content, water activity, and peroxide values we did not find. It's an average of 9 readings. So we did not find anything actually, either change in color or hardness or water activity or peroxide values, but there was a slight change in moisture. You can see the moisture decreased when the treatment time was increased. 10 seconds you were 3.62, but 40 seconds it became 2.89 or 2.9. So there was a slight decrease in the moisture content. Water activity did not change, peroxide values didn't change, and LA and V, there was no significant change. So basically, pulsivy light had no effect on the color, hardness, water activity, and peroxide values. So this is the visual appearance of pecan halves after treatment. You can see here when they're very close, like 4.5 centimeters distance from the light source, we observed some charring. Means they got burnt actually, the surface got burnt, yes. 9.55 cm, 7 cm, they are fine. And this is the control. So you can compare it to the color, it's 4.5 cm, 7 centimeter, you're okay. And 9.5 cm, they're also okay. So 1 second, 3 second, 5 second, 9 second, 12 second, or 15 second, those are treatment times. So what are the limitations of IPL actually? It depends on the food surface, whether they are transparent or they're clear or they're smooth. Pecan surface, they are not smooth. You can see they're not smooth, yes. The composition of food, whether they are high protein or there's a lot of oil in the food. And if you treat it for longer period of time, like for 30 seconds, 60 seconds, or 5 minutes, the temperature of the surface of the food increases actually, yes. These are some of the limitations. So what are the conclusions from our study? The microbial reduction increased with the increase in treatment time, and it decreased when the distance was increased. Time and distance had significant effect. The p-value is less than 0.05 on the reduction, whereas there was no interaction between time and distance. There was no difference. When I say difference, means statistically significant difference in color, hardness of and peroxide values. Yeah. When it comes to water activity, we found that water activity varied from, it's the typical water activity for pecans, standard value actually 0.6 or 0.7 to 0.7. So which is similar to our findings. Yes. And as I mentioned before, the moisture content slightly decreased when we treated for more than 20 seconds. So overall, our study demonstrated that IPL is a promising non-thermal technology to improve the safety and quality of pecans. We have worked before on meat and fresh vegetables and other products. Right now, currently, my lab is working on pecans. So this is a, I hope it will play. Or you might have seen already, so I don't want to play this one. Okay, the video, I think I posted in Facebook, CAT Facebook. So I would like to thank USDA because this was supported by the US Department of Ag, Education and Economics under accession number this. So it's a very big project actually. We are getting about $500,000 per year. And recently we were in USDA in Virginia, to present our work. So there were about 48 submissions, and ours was one of them actually to present. So this is the gang, good engineering. Robin is my postdoctoral scientist, and this is my colleague from Ghana who came and spent 5 weeks in my lab. So he just left 10 days ago for Ghana, and the rest are all are my graduate students. So they come from all over the world, starting from Sri Lanka to Nigeria, Ghana, Egypt, and India, of course. Yes. So this is my partners in crime during my stay at CAT. So thank you very much for your time and attention. And if you have any questions, then I'm willing to answer. Thank you very much again.
Samanuz Babu looks very cute.
So I don't look cute or what you say.
I can't see you. Where are you, actually?
I'm here. I'm here.
Oh, okay, okay, okay. But see, he's in the center, so I was able to, you know, see him immediately. Anyway, um, Jigyasa, go ahead with.
So here we are with the second segment of our tea talk, as we have first is the presentation and second we have our question and answer session. So earlier, our today's panel, actually today's the participants we have, all our experts we have, and so
And then
we are blessed.
just 1 second, 2 second, 2 minute video. I can say.
Thank you, sir. Thank you. That was a good
Thank you very much
overview.
for
Yeah.
your time.
Sir, we have questions from Dr. S.K. Das, sir. Sir has asked that could you please elaborate more on the intensity of pulses and pulse duration?
Pulse duration. I think I mentioned actually during my
Sir, actually, in your presentation, you have mentioned that the pulse duration varied from 1 second to 10 seconds or something like that. But
yeah.
in general, what is the normal recommended pulse duration for the different types of commodities? In general, I'm asking this.
You see, the output is about it's about 505 joules, 500, let's say 500 joules per pulse, and with a duration of 360 microsecond. Okay, so it delivers 3 pulses per second actually. So it depends, how long you are going to treat it. So the pulse will depend on that actually. In some publications they use you can vary the number of pulses. That's also with treatment time. Okay, so if you treat for a longer period of time, then you will have more pulses. But the machine has a fixed pulse actually, has 3 pulses per second. So we cannot change that pulse actually. It's 3 pulses per second. So the number of
And
pulses
my
will
second
depend.
question was actually, you have used one particular equipment. So is that equipment available commercially, or you have developed as per your requirement, particularly that equipment?
No, it is available commercially. Yes. Yes. Actually, they
And
have
that is
come up with a
that is
newer
also
version.
having
So
the provision of your requirements, managing the pulse strain, something like that.
I'm sorry, I didn't get your question.
Actually, the commercially available equipment, so is it sufficient enough or is it adequate enough to maintain the requirements like pulse duration, intensity, all those things?
Yes, they have come up with the one I showed you, the older version. We have a newer version actually, where you can change all this, pulses. And yes, they have. Yeah. So
Sure.
that Genon is the only company in the US which produces that equipment. So yes, because there are some that and only very few schools in the US have this equipment. Ours is one of them. And some people also, you can develop the pulse UV light system. You can, you just have to buy the lamps and all. Actually, we are working with the USDA ARS Byron, which is only 10 minutes away from our school. So they are going to do a commercial scale process. We'll have, here we see just one lamp. So we are going to have a lamp on the top, some different sides, and we'll have a conveyor belt actually where pecans will be moving, and we are trying to also, in this, we are exposing the pecan only on the top surface. So what happens if the E. coli or Salmonella are on the side, on the back,
Sir,
right?
another supplementary query from my side. Sir, most of the
Yes,
times
please.
the type of treatment that we make that depends on the initial microbial load of the commodity. So in your
Yes, that's
particular
right.
case, actually, you have tried to inoculate the microorganisms into the product. So
Yes.
can you give us some idea on what is the normal level of the microorganisms, E. coli or Salmonella available in such type of commodities? In case, suppose you are not treating, then what is the amount of risk that we are having?
You see, a couple of years ago, I attended this UV light system conference, because according to FDA, Food and Drug Administration, US FDA, we need to, if you come up with any type of new processing methods, we are supposed to get a reduction of at least 5 log. So, we didn't get 5 log, we get 2, 3 logs. So I don't know from where they got that 5 logs actually, but in nature, you will never find 5 log, concentration. Yes. It's very less actually. Yes.
As I can see
Anywhere.
that this fruit is completely enclosed, so
Yes.
contamination up to this level, I think it should be rare.
Yes. And in nature, even if they fall on the ground or let's say mangoes or whatever actually, you will never have 7 log actually. It's just
Right, sir.
impossible
Right,
actually.
sir.
Yes. So what we basically they do is, we increase the initial concentration and try to reduce it. So in nature, you will never have 7, 8 log, never. pecan
Yes.
or any other food products. Yes.
And
Yes.
it's also a very good casing actually surrounding the fruit. So I think the level
Mm.
of the microorganisms should be low.
Yeah. So we are trying with USDA, to develop and just like in the industrial scale. So we'll have lights from the top and from the sides and all, and we are going to have a conveyor belt, which we can set so that it can, right now the pecans are only just sitting on the surface, okay, and expose only the top surface. So we are trying to move the pecans so that they can be
Thank you so much,
exposed
sir. I
on
think
all
others
sides.
will be waiting to listen from you. Thank you so much. It was an excellent
Thank you
talk.
very much, Pradesh. Thank you so much.
No, no. So I have a follow-up question from what Sanjay brought up. Is where do farmers grow this pecan so that so much E. coli and Salmonella gets attached to the pecan cells or to the pecan body?
You see, there are big orchards actually. They grow it in
Right,
big, huge orchards in Georgia. I have seen this huge, yes,
right.
hundreds of trees actually. The farm, yes. So it can be anywhere actually, anytime, starting from harvesting to packaging. Okay, mostly the chances are high during harvesting. What they do is they set the trees or branches. When the pecans, insel pecans, they fall from the tree on the soil, okay, on the ground, then they collect them. Okay, so that's where very high
But
chance
but
actually.
why is why, I mean where are what is the place where this Salmonella or E. coli is being produced or is being why is the soil contaminated is what I'm asking really. Is it from the manure or is it from some other
Yeah,
source?
yes, from different sources. It could be from manure. It could be, like irrigation. Like in California, we had a couple of years ago, this fresh greens because there were cattle, and they were
Oh,
trying to irrigate, and the water moved from that place to the farm. So there are many places where it can be contaminated actually, starting from harvesting to all the way to processing. And right now they
okay.
are using actually, all the pecan industry, is very robust, and they are using like hot water pasteurization. They are using steam. They are using dry roasting. So we are trying to do if we can use some non-thermal processing. Yes, it's very strict actually. They do, before particularly as soon as they harvest, they do it with hot water and dry roasting, and also they use some chemical processes like chlorine, organic acids, and all. Yes, the
But
industry is
even
using
after
that.
but even after that you still have these bacterial and viral
Outbreak.
colonies.
Yes, yes, we still have some outbreaks. Yes, although
Oh,
it's rare, but we still have some outbreaks. Yeah, that's right.
okay. Well, that's interesting. Okay.
Sir, we
So
have one more question from Dr. Kalpana Raiguru, ma'am. The
yes,
question is, what is the limitation of IPL application with respect to the moisture content of food products? Is it applicable to high moisture products?
yes, it is applicable to high moisture product. The only limitations are like it works only on the surface. It's basically it's light. So it was very good in liquid products, not products, liquid food like milk. I think the most servings is beer, wine. It will work perfect, because this is basically light, so it can't enter into only certain millimeters or centimeters. Okay, so that's the first limitation. Yes, like if you have a meat, which is 5 inches thick, and if there are E. coli at the bottom, it won't reach. So that's the one. And second one, it depends on the surface, whether it's a smooth surface or it's irregular surface, rough surface. That is another one. But I don't think it's anything to do with the moisture content. Yes.
Sir, in connection to that, I have some exactly that is what I wanted to know how far it is applicable to the liquid food products because that is essentially required for these microbes thing. So in our place, sir, I was going through net simultaneously. I got to know that it is called as this pecan as American walnuts. We have a lot of walnuts, you may be knowing.
Mhm.
And then one more thing, sir, in particularly in Odisha, we have huge quantities of groundnuts where
Mhm.
I think application of this will be suitable, similar with similar composition, whatever for walnut or pecan you have shown.
Yes, it will be suitable. Actually, I saw another question about aflatoxin. Well, one of my
Flat.
students, who,
They are the
yeah,
microbes aspergillus flavors, not exactly the semolina and all that. Some
mhm.
other bacteria you said. So things can be the indicators can be standardized. And what I understand now, the depth of the grain or the product, whatever during the treatment also has to be optimized for efficient
Yes,
application, complete
yes,
application.
yes, yes. That's
Yes, sir.
that's correct.
I have one more question that is doubt, not question. Since it is non-thermal type of application, can we apply this IPL to the grain in container? I mean, along with the packaging material. Is it possible?
Uh, it's possible. It depends on the packaging material. This is basically light. So,
Like,
if it's
Yes.
very thick and if you can't pass through the packaging material, then it's not going to work.
Mm.
So yes, but it's working very good with liquid food actually. In US, they are using already. It's already in use actually.
That is actually a trouble everywhere, sir. For liquid food only, people are searching. We have general PEF, and that way, how actually it is better. You said that it has to be combined with cold plasma. I was thinking of having a comparison between application of cold plasma and IPL separately and their cost with respect to their cost component. When you go for a commercial scale, when we go for this type of thing at a commercial scale, so,
Yes,
but now
yes.
that you are saying that combination of these two is more efficient, so I don't know. Maybe you can just give some light on this if you have time,
Yeah,
sir.
we did also like your question was, like we did for light separately, and we also did with cold plasma. Then we did a combination of them. Okay, so when we combined cold
Mhm.
plasma with light, then we got higher reduction actually. Yes. And yes, so I can send you the paper, but we haven't done the economic study, okay, whether it's economical or not, we didn't do that, okay.
Sir,
And
actually,
coming,
in country like India, we always keep that as a basic part every time.
yes,
This is the way we consider because we have huge quantities of everything. But this is a very nice area on which we got enlightened. We didn't know about it. At least I didn't know. So thank you so much for this nice. Just that I am available today for this for to be a part of this talk. Thank you so much, sir.
this is not only pulse light, we are working on the blue light. We just bought an equipment, blue light. One of my student is working with milk powder. Then we have just ordered another equipment. My lab is now light based. So you are ordering another equipment where you can change the wavelength actually. You can have different wavelengths. You can have
And
combination of
that can be
wavelengths.
optimized. Huh? That
Then
can be optimized.
optimize. Yes.
Mm.
And
And sir,
about
that
after,
mm.
yes, please. Please go
And
ahead.
Debhai was asking that one from where they come. These bacteria are in our place production harvesting. It may not have, but if we do not use an efficient drying system,
Yes.
when the moisture content is very high, there is likely that the grains or the nuts they get contaminated with different types of bacteria, fungi. In India, this is quite I can say intensified because we have not yet developed very efficient drying systems to be dried at a larger scale. So we get to face such type of problem. In your place, maybe you have those doubts, but this will be useful. But it has to be studied here also, and the standards have to be found out. Then I think it will be a good help because we are looking forward to non-thermal processes, particularly for oil seeds and others. Thank you,
See,
sir.
Yes.
Kalpana,
Sir,
long time back, people used to do drying, right? Put chhata upare pakai diyo, the solar drying, right? and
sir.
that's how the microbes were eliminated, right?
Mm.
It took a long time. I'm not denying that, but the basic underlying thing is that moisture should be removed. If there is moisture, then there will be microbe or
Yes, yes,
fungi or whatever it is.
yes, yes, yes.
If we leave it in the dark place in our closet, even food materials catch fungi, right?
Mm-hmm.
So the system that maybe is developing new now is less time consuming. Do it little with a little bit of cost. Can we get this thing into the market quickly? So the whole idea is business driven, not
Yes, sir,
necessarily because,
absolutely, absolutely.
Yes.
right? Okay,
Um,
but my question to Ajit Babu is, and this is a follow-up from Kalpana's, is UVC that can penetrate packages very easily because it has shorter wavelength, and that can penetrate through the packages real easily. But the whole idea is once it penetrates, it loses its the wavelength short lengthens.
Yes.
So now that it will produce the heat. Okay, which is okay in my opinion, because the heat can then act on the microbes and other stuff. Have you compared, and this is a question, the other end of the spectrum, not visible or hyper visible spectrum, microwave. We have microwave. Have you compared microwave based um, reduction of microorganism versus, let us say, UVC or UVA, whatever you are doing now, or blue light?
No, we haven't done with micro, but we are trying to do actually because like there was one question about aflatoxin. So right now we are working, two of my students from Ghana, they are working on, one is working on sorghum and another one is working on peanuts. Peanuts. So they are trying to inactivate or control aflatoxin using pulses like one is working on peanuts and another one is working in sorghum. But we are also trying to, we'll do with microwave. Yes, we haven't done that.
That
We
is
haven't
actually,
compared it.
sir, sir, microwave actually is a thermal process. There
Yes.
are reports in India, few people have worked here, and I was going through. There is a change in the, sir, the fat profile on peanut
Yeah.
only, because it is a thermal process. It is there is some effect. So I found this non-thermal process can help maybe in a better way, definitely what it says. But microwave also, if it can be done in a very standardized way and limited way, confined way to protect that part. Otherwise, there is a change in fat profile, which lipid
Yes.
profile, I mean, which have been found by a few scientists. And germination, one of my students also tried germination percentage. We are losing the germination by microwave heating. Otherwise, the grains are, we are keeping the grains actually to for a larger extent. They self like we are enhancing, but there is a huge loss in germination that we have found.
No,
And
Kalpana,
Microwave.
listen. The ultraviolet light is, when you say non-thermal or what Ajit Babu is calling non-thermal, the source of the pulse is non-thermal, but non-thermal processes don't kill microbes. They have to produce heat to reduce the microbe population. Okay, so whether you use microwave or ultraviolet pulse, they have to be converted to heat energy in order to reduce the microorganism. Am I right, Ajit Babu, or I'm wrong?
no, they don't produce a lot of heat. So heat is not the main cause of killing or inactivating bacteria. Non-thermal processing, no. Only thermal processing, they produce a lot of heat. So non-thermal heat is not the main cause. It produces some heat, yes, in the product, but heat is not the main cause. Yes. If you look
Okay.
at the different principles, it's sort of physical, photochemical, and so on, which has got a different mechanism actually. Yes. Yeah.
So sorry, I back off.
And
Well,
now
any other questions?
we have now working on blue light and all different types of lights actually, yes, and in combination and with different products.
Sir,
Okay.
if you have any brief notes on these light application and blue light application, sir, if you can post it in CAT, maybe we all can get that and go through, get some knowledge. This mechanism.
Yeah, sure. Yeah.
So
And
all
if you
these
can, yeah, if you can send me your email on the email, I can all the publications I can send it to you
that I
and
will
all
send.
this.
Yes, sure, sir. That I will send. That I will send.
And I teach food safety, so I can also share my PowerPoints, class notes and all if you are interested.
Yes,
I'm
sure,
okay
sir.
with
Thank you. It will be most useful for us.
it.
Sir, there is a question from Dr. Fakir Mohan Sahu. Do you want to ask that question, Dr. Sahu?
I think it was about aflatoxin. I saw. I think it was on the chart. No.
No. Dr. Sahu, you are muted, but if you want to ask the question, you can unmute and ask. Dr. Fakir Mohan Sahu. Okay, he has left. No, he's here. So the question is, before exporting to India, is pecan always treated with any thermal or non-thermal process? Oh yeah, he's now online. Okay, you can ask the questions.
Fakir, unmute yourself.
Dr. Sahu, you have to unmute yourself. Yes.
Yeah. Am I audible, sir?
Yes.
Yes.
Go ahead, ask the question. Oh, he's having trouble, I think. So I'm asking the question anyway. Is pecan always treated with any thermal or non-thermal process to ensure zero contamination of Salmonella and E. coli before exporting to India?
Yes. They have a very high standard actually, pecan industry. So what they use right now is, I think I mentioned, they use conventional thermal or chemical decontamination methods. One of them is like they use hot water. So they use hot water, they soak the pecans for a certain number of hours or minutes, and they also use steam. They use dry roasting and chemical method. They use chlorine, organic acids, and yes, they are treated. Yes, I'm not sure whether they treat with light. I don't think they treat with light, but they are treated. Yes.
Okay.
They are treated. Yes.
All
but
right.
Right now we are exporting only pecan halves, and we are not allowed to export in-cell pecans. Yes.
Okay. Any other final questions before Jigyasa takes over? Kalpana, you have any? Sanjay or anybody else? All right. Hearing none. Jigyasa, it's all yours.
So I think we have completed that impact of aflatoxins.
Sorry.
Have we discussed on that impact of by J.K. Saucer? The last questions. Have we taken that, or sir would like to?
Yes, right now we are working on it, so I don't have any results or anything to share. We are trying to control inactivate aflatoxin on peanuts and sorghum using pulse UV like this. So two of my students are working now, so probably in the future, I can share some results, and yes, but it's working actually. We are getting about 12% to 70-80% reduction in aflatoxin. Yes. But we have just started. These two students joined last semester, so they are working on it.
Sir, there are two aspects to this question. First of all, actually, your research actually is basically on two aspects. One is on pecan, the other one is on the IPL system. So the first question will be, suppose as Fakir asked, the type of the commodities that you are sending to India, so are they having some aflatoxin level? Is your study saying that actually they're also having some aflatoxin level which need to be reduced? And second, as we have already been discussing, is the IPL having that potential to reduce the aflatoxin level to some extent? May not be with the pecan seeds, but some other commodities.
Yes. You see, when we export from here, from US, they are very stringent conditions. Okay, so it will never go with aflatoxin. In Europe, I think they are more strict. I think in US it's allowed 20 ppb, but US it is 2 or something. So yes, we don't send stuff with aflatoxin. Yeah. Yes, they do all
There are
kinds of
international
treatments and
standards.
also
There are international
yes,
standards.
international standard. When you are
Standards are
trying to
there, and that
export,
was there.
import, yes, export or import, yes. But this is very prevalent in Ghana actually. It's a big problem in Ghana with corn, sorghum, and also this project is with I'm working with USDA and Ghana. So we are developing. In fact, Dr. Suranjan, from CAIT, I'm a junior. He's trying to develop a sensor which can quantify aflatoxin level. It can be used in the field. We are trying to make it very low cost, very cheap, so that even farmers in our world, like Ghana and Africa, they can use it in the field during storage. Yes. So aflatoxin, we are still working on it. So I don't have any, solid results that I can share with you. But we are working on it. Yes. So in 2 products, actually,
Thank you,
sorghum
sir.
and
Thank you
peanut.
so much.
Yes. Yes, sorghum and peanut. So once the sensor is developed, I'm going to take it to Ghana and we test it in the field and farmers field and give storage in the.
So Jigyasa, you may take over now.
Here we are at the end of today's talk and discussion. We had a wonderful discussion with Dr. Ajit Mahapatra sir and all our participants. So I would like to thank sir for this discussion and everybody present over here. And I would also like the viewers who are watching us in the YouTube also to post their doubts or any queries and comments in our comment section. So that's all about today's session. Here we are concluding it. Thank you. You all.
Jigyasa, I have a few words for you. You didn't introduce yourself. So I know everybody else except you, actually. So.
Sir, I'm glad. Sir, I am Jigyasha Bal. I have completed my BTech from CAT Bhubaneswar. I'm a 2018-22 batch. Currently, I'm a PhD student of Renewable Energy Engineering at MPUT Udaipur, Rajasthan.
Oh, okay. Mhm. Good.
Thank you.
So I'm traveling to South Africa, Pretoria next Thursday. So wish me luck. So.
Yeah, good luck, good
Good
luck.
Good
luck,
luck,
sir.
sir.
Good
Good
luck.
luck, sir.
Don't fly through Middle East. Now there is war. Okay, sir. Thank you. Thank you very much for
Thank
the
you so
talk.
much.